Welcome back. We are doing notes 2.2 now. For the warm-up, I already filled this in, so you can go ahead and see how you did fill in these answers if you didn't get them. Just the list of perfect squares that you know, so hopefully you know at least the first 10. Just a shortcut in your calculator to get all of the perfect squares. I highlighted it in pink here, but you can go to y equals and type in x squared, and it will give you a list of your perfect squares in the table. So if I go to y equals and do x squared, second graph to get my table, all of these y values starting at 0 are your perfect squares. So I stopped at 225, which is 15 squared, but you can see that 16 squared would be 256, 17 squared would be 289, 18 squared is 324, 19 squared is 361, 20 squared is 400, and so on. So this is a list, and it's going to go on forever, and well, until your calculator runs out of room. But it's going to give you as many perfect squares as it can. So if you're ever stuck and forgetful, then just keep that in mind. So we are going to learn how to work with radicals today. We actually did this back in Algebra 1. It's been a while, so we're going to review it, and we're going to do more complicated examples than we did in Algebra 1. So the first rule of square roots is never leave a perfect square under a radical. And you can see it says reduce the square root of 32. The reason I can reduce the square root of 32 is because I know that 32 can be rewritten as 16 times 2. And the reason why we would be able to do that, and the reason why we would want to do that, is because 16 is a perfect square. So I actually know the square root of 16. The square root of 16 is just a 4. It's a perfect square, so it gets released from the radical. But 2 is not on our list up here of perfect squares. 2 cannot leave the radical because it's not perfect. So this reduces to 4 times the square root of 2. So we'll keep working with these examples today. So reduce the square root of 72. Well, I know that 72 can actually be rewritten as 36 times 2. And the reason I chose 36 is because 36 is a perfect square. It's on my list up here. And since 36 is a perfect square, it gets released from the radical. The square root of 36 is 6. 2, however, is not a perfect square, so 2 is trapped in the radical. You can only leave the perfect square if you are perfect. So the square root of 36, since 36 is perfect, it gets to leave, and it leaves as a 6, but the 2 is stuck. Now, what a lot of people do when they are reducing is they find perfect squares that go into our number in question, but they don't actually pick the biggest perfect square. So a rule of thumb is you always want to pick the biggest perfect square. You can still do it if you pick a perfect square that's smaller than the biggest one, but you're going to have to do a little bit more work. So I'm going to show you 2 ways that we can reduce the square root of 80. So on the left here, we're going to do the biggest perfect square. And then on the right, we're going to do the not biggest perfect square. So I know that the biggest perfect square that goes into 80 is 16. It is 16 times 5. Well, the square root of 16, that's 4. And 5 is not a perfect square, so 5 is stuck. So this reduces to 5 times the square root of 5. Sorry, 4 times the square root of 5. Well, some people might see 80 and they know that 4 is that most popular perfect square. They know 4 goes into 80. So some might write, okay, well, this is actually 4 times 20, which is true. 4 times 20 is 80, and 4 is a perfect square, so that can come out, and the square root of 4 is 2. So I could rewrite this as 2 times the square root of 20, but we're not done because 20, I can actually break down 20 using another perfect square. So I have this 2 already out front, and I can say, well, hey, 20 is actually 4 times 5. So I was able to pull out another perfect square. The square root of 4 is 2 again. So I had the 2 out front already. I had this 2 already out front. And now I have another 2 because the square root of 4 gave me another 2. And that 5 is trapped in. And hey, 2 times 2 is 4. So I get 4 square root of 5, which is the same answer we got over here. It just was a lot faster to get this one. So that's why you always want to use the biggest perfect square possible. So the way that I always tell my students to do this is with your list of perfect squares, start dividing. Just start at the perfect square that is the biggest perfect square smaller than your number. So the biggest perfect square smaller than 8. So the biggest perfect square smaller than 8 would be a 4. So let's see, well, can 8 be divided by 4? Hopefully you know that yes, it can be. 8 divided by 4 is 2. So I can rewrite 8 as 4 times 2. That's a true statement, right? Because 4 times 2 does in fact equal 8. The reason I want to rewrite it like this, though, is because I can take the square root of 4 now, because that's a perfect square. The square root of 4 equals 2. But the other 2, the 2 that's already under the radical, doesn't get to leave because it's not a perfect square. So I get 2 on the outside and a 2 trapped on the inside. So the square root of 8 is actually, in simplified form, as 2 square root of 2. 12. So I'm going to start with the biggest perfect square smaller than 12. So I go back up to my list. The biggest perfect square smaller than 12. Well, that would be 9 because 12 falls right here in between 9 and 16. So the biggest one smaller than 12 would be a 9. So I go to my calculator and I say, okay, can I divide 12 by 9? 12 divided by 9. Oh, no, I get a decimal. So 9 is not going to work. So that's where I move to the next perfect square. So 9 didn't work, so I try my next one, which is 4. All right, let's try that. 12 divided by 4. It does. 12 divided by 4 is 3. So what I can do is rewrite this 12 as 4 times 3. That's a true statement. 4 times 3 is in fact 12. But the reason why I wanted to do this is because 4 is a perfect square. So that gets to leave the radical. It comes out as a 2. 3 is not a perfect square. So 3 is stuck. So this gives me 2 square root of 3. So your goal is to get as much stuff out of that radical as possible. So that's why we are rewriting our number using factors. So 12, the factors of 12 are 4 times 3. And the reason I chose 4 and 3 is because 4 is a perfect square. What a lot of people do on accident, and they're just trying to find numbers that multiply to 12. So a lot of people for this would say, well, 6 times 2 is 12, which is true, but this isn't helpful because neither of these are perfect squares. These are not perfect squares. And the only time you can pull something out of a radical is if it's a perfect square. So we don't want to use numbers like 6 and 2 because 6 and 2, neither of those are perfect squares. Whereas the 4 and the 3, 4 times 3 still equals 12. And since 4 is a perfect square, I was able to remove it from the radical as a 2. So 20 is up next. So the biggest perfect square is smaller than 20. Well, the biggest perfect square is smaller than 20. 20 falls right in between 16 and 25. So it would be 16. Well, hopefully you already know that 20 can't be divided by 16, but if you're not sure, you can just type it in your calculator. If you get a decimal, that's bad. So 16 is not the winner here, so I'd move to the next one. So it's not 16, so the next one smaller would be 9. Well, hopefully you already know 20 can't be divided by 9, but if you're not sure, just do 20 divided by 9. You get a decimal, so we move on to the next one, which would be 4. You should know that 20 divided by 4 equals 5. So I can rewrite this as 4 times 5. And this is good because 4 is a perfect square. The square root of 4 is 2. And 5 is not a perfect square, so 5 is trapped. So my answer is 2 square root of 5. The biggest perfect square that goes into 24 is 4. And it's 4 times 6. So again, a lot of people would say, well, wait, 12 times 2 is 24, which you're right, but neither of those are perfect squares. Not PS, they're not perfect squares. So that's not going to work. You want to make sure you're using perfect squares for this. So 4 is a perfect square, so it gets reduced because the square root of 4 equals 2. So I get 2 square root of 6. 6 isn't a perfect square, and it can't be reduced using any perfect squares, so it's stuck forever. 28. So the biggest perfect square smaller than 28, 28 would fall right here. I hope it's pretty obvious that 28 can't be divided by 25. 28 also can't be divided by 16, and again, if you're not sure, just type it in. 28 divided by 16 gives me a decimal. The next one would be 9. 28 divided by 9 gives me a decimal. The next perfect square smaller than 9 is 4, so 28 divided by 4 gives me 7. So this is going to be 4 times 7. So this is the square root of 4 times 7. We like 4 because it's a perfect square. The square root of 4 is 2. We don't like 7 because it's not a perfect square, so it is trapped underneath the radical. So we get 2 square root of 7. Well, the biggest perfect square smaller than 18 is 16, but 16 can't go in evenly to 18, so it's not 16, which brings us to the next one, which is 9. 9 times 2 is 18. Hopefully you know that. And I know the square root of 9 is 3, because 3 times 3 is 9. So this gives me 3 square root of 2. 2 is trapped because it's not perfect. 27. Well, the biggest perfect square that goes into 27 is 9. 9 times 3. Well, the square root of 9 is 3. And my other 3 is trapped because it's not a perfect square. So it was the square root of 9, which gave me the 3, and then the other 3, which is trapped because 3 is not a perfect square. 45. Well, that's the square root of 9 times 5. Square root of 9 is 3, again, and 5 is trapped. So I get 3 from the square root of 9, and then 5 is trapped underneath the square root. So I get 3 square root of 5. 63. Well, if we keep doing it the method before, I have 63, which falls right here. So the biggest perfect square smaller than 63 would be 49. Hopefully you know that 63 can't be divided by 49. You get a decimal. The next perfect square smaller than 49 is 36. So 63 divided by 36. I get a decimal. The next one would be 25. So 63 divided by 25. Decimal. And then next would be 16. 63 divided by 16. Decimal. So next up is 9. 63 divided by 9. I get 7. So 9 is the winner. It's 9 times 7. The square root of 9 is 3. 7 is not a perfect square, so it is trapped. 108. Well, if I go to my list, 108 would fall right here. The biggest perfect square smaller than 108 is 100. I think it's pretty obvious that you can't divide 108 by 100. So I'm going to move on to the next one. I also think it's pretty obvious you can't divide 108 by 81 or by 64. 108 divided by 81, decimal. 108 divided by 64, decimal. So the next one would be 49, decimal. 108 divided by my next one's 36. That one works. So it's 36 times 3. So this is 36 times 3. We like 36 because it's a perfect square. The square root of 36 is 6. But 3 is trapped because it's not a perfect square. So I get 6 times the square root of 3. 48. 48 would fall right before 49. So my perfect squares smaller are these guys. Again, hopefully you know 48 can't be divided by 36, and 48 can't be divided by 25, but you can test them out in your calculator if you're not sure. So let's try 16. 48 divided by 16. I get 3. So 16 times 3 equals 48. So I can rewrite this as 16 times 3. And 16 is a perfect square, so that gets released as a 4, but 3 is trapped. So I get 4 square root of 3. And finally for this page is 80, which we already did 80, same one from up here. So we're going to use the biggest perfect square, which is 16. It's 16 times 5, so that gives me 4 square root of 5. For the next 3, we're going to look at what happens when you have a number out front already. So we already did 12. We said 12 was the square root of 4 times 3. But we have a 6 out front, so that 6 is just going to hang out front. I can do the square root of 4. That gives me a 2. Since I already have a 6 out front, those two are going to be multiplied together. And then the 3 is trapped underneath afterwards. So I had the 6 that was already out front. That stays out front. And I'm going to multiply it to what came out of the radical, which was a 2. So that gives me 12 square root of 3. $200, well, the biggest perfect square that goes into 200, hopefully you can recognize, is 100, because that is 100 times 2, with that 3 out front. The square root of 100 is 10, and then the 2 is trapped. So I get 10 square root of 2, but I already had that 3 out front, so I have to multiply that to the 10. So 3 times 10 is 30. So this gives me 30 square root of 2. And then 147. So 147 falls right here. So if you work your way down, you can start dividing. You'll see that none of these are going to work until we get to 147 divided by 49. So 49 is our biggest perfect square. So it's 49 times 3. So I can rewrite this as 4 times the square root of 49 times 3. Which 49 is good, 3 is not, and there's already a 4 out front. So that gives me 4 out front. The square root of 49, which is 7, so that 7 joins that 4 out front, and then the 3 is still trapped. So 4 times 7 gives me 28. So this gives me 28 square root of 3. So that's how you reduce radicals with just numbers. Now we're going to focus on reducing variables. With square roots, the goal is to have even exponents. Square roots and even exponents cancel each other out. So the square root of x squared just equals x. The square root of y cubed, well, only even exponents can get released. So what I want to do is rewrite this using even exponents. If you remember exponent rules, we add exponents when multiplying. So I can rewrite this as y squared times y to the first, because according to that rule, since I'm multiplying, I would just add my exponents together, and 2 plus 1 would give me that 3. So these are equivalent. They're the exact same thing. They just look different. And I can use this to my advantage now because I have an even exponent underneath a square root. So it gets released. So this is really just saying, okay, I'm doing the square root of y squared times the square root of y to the first. And the square root of y squared is just y. And then the square root of y, well, that's not an even exponent, so that's trapped. So I get y square root of y. Z to the fourth, it's an even exponent, so it can come out right away. So I'm telling you the square root of z to the fourth is equal to z squared, but I'll show you why. Using that rule from the last problem, I could rewrite this as z squared times z squared. So now each of these can come out because they each have an exponent of 2. So the square root of z squared is z, so that comes out. And then this one can also come out, so I've got two z's that came out, and z times z equals z squared. Number 4, n to the fifth. That's not even, but what I can do is rewrite this as n to the fourth times n to the first. The square root of n to the fourth is going to give me n squared. And the square root of n to the first, well, that is trapped. So I get the square root, I get n squared times the square root of n. And number 5, m to the 10th power. I'm telling you now that equals m to the 5th, but I'll show you why. I could rewrite this as m squared times m squared times m squared times m squared times m squared, because those all add up to 10. And each of these separately can be square rooted because they all have an exponent of 2. So they each come out as an m. And if I've got 5 of them all coming out as their own m, well, altogether that gives me m to the 5th, which is what we got up here. So then what we do is kind of combine our variables with our numbers. So this beast, we've got the square root of 200 x cubed y to the 6th z. What I would do is break this up so that we've got the numbers and the letters all separated. So I'd say, okay, this is the square root of 200. This is the square root of x squared, x cubed, which I need to rewrite as x squared x first because I need even exponents, or more specifically 2. Then y to the 6th, well, that's already even. So that's already, I should know the answer, but if you forget that rule, just make it all multiples of 2. 2 plus 2 plus 2 is 6. And then z, I can't change z. There's no exponent. It's an imaginary 1, which I can't break down a 1, so that's going to be trapped forever. So now 200 we should know as 100 times 2. 100 is a perfect square, so that gets to come out as a 10. So 10 square root of 2 is what the square root of 200 gives me. Then I have the square root of x squared, which that is a perfect square, so that gets to come out as an x. But my x to the first is trapped. So I get x and then the square root of x. All 3 of these get released as 3 separate y's because they all have an exponent of 2. And all 3 of them combined gives me y cubed. You can skip this step though, because if you figured out the rule, when you're square rooting a variable with an exponent, you're just dividing the exponent by 2, and that's what gets released. And then I have just z, the square root of z. You can't reduce that z to the first, so it's trapped. So that comes down and it stays underneath. So altogether, outside I have 10x and y cubed. And then underneath, I have 2x and z. So that gives us our answer. Number 7, I've got a 3 out front already, so that's on the outside. That's going to stay on the outside. I'm going to break the rest of it up. So 56, Well, let's go back to our list of perfect squares. So we've got 1, 4, 9, 16, 25, 36, 49, 64. So 56 would fall in between 49 and 64. So I'm going to work my way down with dividing. I know 56 can't be divided by 49. I know 56 can't be divided by 36. I know 56 can't be divided by 25. So let's try 16. 56 divided by 16. I get a decimal. So the next one would be 9. So 56 divided by 9. I get a decimal. So my next one would be 4. 56 divided by 4. 14. So I get 4 times 14. So this is 4 times 14. That's what the square root of 56 gives me. M to the 4th, that's already an even exponent, so that's good to go. N to the 7th, 7 is not an even exponent, so I need to switch this to n to the 6th, n to the 1st. Because I want even exponents. So then I just got to figure out what gets to be freed and what has to stay. So the square root of 4 gets freed as a 2 because it's a perfect square, but 14 is trapped because it's not a perfect square. And I can't break down 14 using any of my perfect squares. M to the 4th, the square root of m to the 4th, it's an even exponent, so it gets released. The square root of m to the 4th is m squared. The square root of n to the 6th, again, if you remember my rule, if you're square rooting something with an even exponent, you just divide the exponent by 2. So 6 divided by 2 is 3. So that's n cubed. But I still have the other n that is trapped underneath. And you could put the imaginary one, but you don't have to. So altogether, outside, I have this 3 from the beginning and a 2. 3 times 2 is going to give me 6. Then I've got the m squared and the n cubed. So 6m squared n cubed. And trapped underneath, I've got a 14 and an n. So 14n. So that is my answer. Number 8, I've got 2D trapped outside, so that's going to stay out there. I've got 243. So 243, if I look at my list of perfect squares, the next smallest perfect square would be 225. So I'm going to try dividing 243 by 225, but I know that's not going to work. I know that 196 is not going to work, and then you just keep working your way down. 169 doesn't divide it. You can't divide 243 by 144. You can't divide it by 121. You can't divide it by 100. The first one that actually gives you an even answer, or not even, but an answer without an decimal is 81. It's 81 times 3. So 243 divided by 81. I get 81 times 3. So I'm going to rewrite this as 81 times 3. A squared is good to go because it's already an even exponent. B to the 4th is good to go because it's already an even exponent. And c squared is good to go because it's already an even exponent. So all I have to do is square root the 81, which is 9. Then the 3 is trapped. Then I can square root a squared, which is just a, because remember you're dividing your exponent by 2. And 2 divided by 2 is 1. Then I square root b to the 4th, so that gives me b squared. And then I square root c to the 12th, which gives me c to the 6th. So altogether outside, I had 2 and 9, which multiply to give me 18. Then I've got d, a, b squared, c to the 6th. I'm going to put those in alphabetical order. So it goes a, b squared, c to the 6th, and then d. And then trapped underneath, all I have underneath there is that 3. That's it. So that's our answer. The second rule of square roots, never leave a fraction under a radical. So we can break up division underneath a radical by using two separate radicals. So the square root of a divided by b is actually equal to the square root of a divided by the square root of b. So we can use that to our advantage while we are trying to break all of this down. So let's separate this out. This is equal to the square root of 242 x to the 5th over the square root of 25 y to the 4th. Well, we love that denominator because look, we already got a perfect square with the 25 and a perfect square with the y to the 4th. Those can both be released right away. The square root of 25 is 5, and the square root of y to the 4th is y squared. So our denominator is already taken care of. With our numerator, we do have to do a little bit of rewriting here because 242 is not a perfect square. Once you go through all the division with all of that list of perfect squares, the biggest perfect square that goes into 242 is 121. It's 121 times 2. And then x to the 5th needs to be broken down because I want even exponents, so it's x to the 4th times x to the 1st. So now the square root of 121 will get released, and the square root of x to the 4th will get released. So this is going to give me 11 on the outside, but the 2 is still trapped. Then I have x squared on the outside, but the x is still trapped. And that still has that 5y squared on the bottom. So now I just need to combine my things to make this look a little nicer. So I've got 11 and x squared on the outside. And then I've got 2 and x on the inside with that 5y squared underneath. Number 10, you can separate it and go through the steps like we just did, but number 10 is actually nice because I can do 64 divided by 16. 64 divided by 16 is just 4. And I can also do a squared divided by a. If you remember, when you divide, you subtract your exponents. So a to the 12th divided by a is just a to the 11th. So I don't even have a fraction anymore because I did my division. And now what happens, that equals that, is my square root of 4 is good to go because it's a perfect square. But I need to rewrite a to the 11th because I need even exponents. So that would be 10 plus 1. So a to the 10th times a to the 1st. So square root of 4 is good to go. Square root of a to the 10th is good to go. So square root of 4 is 2. Square root of a to the 10th is a to the 5th. And then a to the 1st is still trapped underneath. Number 11, we've got 7 km over 225 m to the 5th n to the 7th. So to clean this up a little bit, if I've got m on top and 5 m's on bottom, this m can cancel out with one of the m's down here, changing this to a 4. And this n can cancel out with one of the n's down here, changing that to a 6. So to make it a little easier, I got rid of 2 of the variables on the top. So what I'm going to do is separate this. So we can say the square root of 7k over the square root of 225, the square root of m to the 4th, and the square root of n to the 6th. The reason why I left the numerator underneath the radicals together is because 7 and k, neither of those are perfect squares, so those are going to be trapped anyways. But my denominator, we've got some goods here. We've got the square root of 225, which is a perfect square. We've got m to the 4th, it's an even exponent, so it's a perfect square. And we've got n to the 6th, which is an even exponent, so it's a perfect square. So altogether, this gives me the square root of 7k over the square root of 225 is 15. The square root of m to the 4th is m squared, and the square root of n to the 6th is n cubed. The third rule of square roots, never leave a negative under a radical. So what we can do to rewrite this a little bit is to pull the negative away from the 25. So really negative 25 comes from doing negative 1 times 25. So we're going to separate this as the square root of negative 1 times 25, x squared. So when I separate all of this, I get the square root of negative 1 times the square root of 25 times the square root of x squared. Well, 25 is a perfect square and x squared is a perfect square. So that gives me the square root of negative 1 times 5x. And so what we're doing is trying to figure out what's the square root of negative 1. So that's what we're going to do now. So it says, surprise, meet your new imaginary friend. Your imaginary friend is called I. Your new imaginary friend is I. I is equal to the square root of negative 1. This is a fact. This needs to be known. I is equal to the square root of negative 1. Your calculator is not going to tell you that. You need to know that. So when I have the negative 25x squared under the square root, well, I can square root the 25 as a 5, and I can square root the x squared as an x. But the square root of that negative 1 gives us I. So this answer would be 5xi or 5ix, however you want to write it. But that I needs to be in the answer. So with number 12, I have the square root of negative 17x squared. Well, 17 is doomed. You can't break down 17 using any perfect square, so that's trapped. So I have negative 1. That's where the negative came from. I have the square root of 17, and I have the square root of x squared. Like I said, 17's trapped. You can't reduce that. Square root of x squared is good, though, because x squared is a perfect square. And then the square root of negative 1, that's where I get my I. So that's I. This is trapped, and then this is x. So on the outside, I have ix, or xi, and on the inside, I have 17. Number 13, sorry. I've got a 10 out front, so that's going to stay. The square root of the negative is going to give me the I. 98 is going to give me 49 times 2. A cubed, well, that's a squared times a to the first. And b to the eighth is already an even exponent, so that one's good to go. So this one's good. Then I've got the a squared. I've got the square root of 49. The 2 is going to be trapped, and the a to the first is going to be trapped. So I have 10 and I on the outside. Then I get a 7. And then the square root of 2 is trapped. Then I get an a on the outside because the square root of a squared is a. And then the other a is trapped. And then I've got the b to the fourth because the square root of b to the eighth is b to the fourth. So these guys are freed and on the outside. And then I have the 2 and the a on the inside. So altogether I get 10i times 7. So that's 70i a b to the fourth. Those are all my things from the outside. And then underneath I've got 2a. Number 34. Well, first up, I've got the negative. That's giving me an I. In the numerator, I've got a square root of 3 and then the square root of y to the fourth. In the denominator, I've got the square root of 64. Good news, we've got y to the fourth, which is perfect square because it's an even exponent. And I've got 64, which is the perfect square because that's 8 times 8. So I've only got that 3 that's going to be trapped. So I can rewrite this as I, and then the square root of 3 times y squared over 8. So the nicest way we can write this is just in one fraction. I can move this I, technically it's I over 1. So I can move that I to the numerator with the rest of the stuff. So I would write this as I y squared, square root of 3, because we like to have our radicals at the end, divided by 8. Number 15, the negative's giving me an I. 243, we did this in another problem recently. It's 81 times 3. K is not even, but we also can't reduce it, so that's trapped. Same thing with M, but N squared is good because it's even. So that's going to come out, and the 81 is going to come out. These three guys are going to be trapped. So this is going to give me a 9. This is going to give me an N. So those have been released with the I. The I is also outside. So I can say this is 9 Ni or IN. And then underneath I had the 3, the K, and the M. That couldn't come out. Number 16, the negative is giving me the I. Then we have the square root of 19. Well, 19 can't be reduced. It's a prime number, so you can't divide it by any of the perfect squares. Then same thing, x can't be reduced because it doesn't have an even exponent, and you can't break down the 1, the imaginary 1. Y cubed can be rewritten as y squared times y to the first. And then my denominator is 100. So this is good and this is good, but these three are bad, and then that I stays outside. So this gives me IY squared. Nope, sorry, IY. The square root of y squared gives me y. And then we had 19x and y trapped underneath. Those have to stay. And on bottom, the square root of 100 is 10. So that is our answer. And last one on this page, we have number 7. We have number 17. So we've got a 7 out front. We've got a negative under the radical, which is going to bring out an I. We've got the square root of 400, which is actually a perfect square. We've got x squared, which is also a perfect square. We've got y to the 4th, which is also a perfect square because these all have even exponents. And then z to the 8th, which is also a perfect square. So this is good, this is good, this is good, and this is good. They all get released. The square root of 400 is 20. The square root of x squared is x. The square root of y to the 4th is y squared. And the square root of z to the 8th is z to the 4th. So everything's on the outside. So I just have to put it all together. So 7 times 20 is 140. Then we have the I, and then we have x, y squared, z to the 4th. Our last page, the powers of I. This is a little diagram that I suggest you memorize. I added this extra stuff here to show you that it keeps going on forever. So write this stuff down in pink. So I to the 4th equals 1. I is just I. That was the square root of negative 1. I squared actually just ends up equaling negative 1. And I to the 3rd equals negative I. And it keeps going. So after 4 would be I to the 5th, which would fall to I. I to the 6th would fall to negative 1. I to the 7th would fall to negative I. I to the 8th would fall to 1. And keep going. I to the 9th, that falls to I. I to the 10th, that falls to negative 1. I to the 11th, that falls to negative I. I to the 12th falls to 1. And it keeps on going. So memorize that diagram, or you can memorize it like this. I is just I squared is negative 1. I cubed is negative I to the 4th is 1. And then it keeps going. So I to the 5th would be I to the 6th would be negative 1. I to the 7th would be negative I to the 8th would be 1, and so on. So this says write as an integer or a single power of I. So either your answer is going to be a single power of I, or it's going to be just a nice number. So this, I mean, same rules apply. You add your exponents when you're multiplying. So that really gives me I to the 7th. And if you wanted to follow this chart and just keep going, you know I to the 4th would be here. So it would go I to the 5th, I to the 6th, I to the 7th would fall here, which is negative I. So I know that this is going to equal negative I. The other ways that you could do it is you could break this down and say, okay, well, I to the 5th is I to the 4th times I. And I squared. So according to the thing that you should memorize, I to the 4th is 1. I is just I, so it's 1 times I. And then I squared, according to the thing you should memorize, is negative 1. So 1 times I times negative 1 equals negative I. But we got that already because we just kept going with our chart over here. So number 19, well, we know I squared times I squared is just I to the 4th because you add your exponents, and I to the 4th is 1 according to our diagram. But we could also do it this way. I know I squared, or hopefully you know I squared is negative 1. And then it's another negative 1. So negative 1 times negative 1 equals positive 1. I to the 10th times I to the 5th. Well, that's, I mean, I to the 10th is really just I squared times I squared times I squared times I squared times I squared. And I to the 5th is I squared times I squared times I. So each I squared gives me a negative 1. So it's negative 1 times 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 I. So I get those cancel to give me a positive. These two cancel to give me a positive. These two cancel to give me a positive. So I'm left with just negative I. Or you could remember, okay, I add my exponents, so this is I to the 15th. And then you could just keep the pattern going. So we'd stop at 4, so it'd go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 would fall here, which is negative I. I to the 4th squared. Well, this is the power to a power rule, which is where you multiply. So this is I to the 8th. But really, you should know I to the 4th is 1, and 1 squared is just 1. Or you could do I to the 8th and then just keep it going. You know, 4 stops here, so it'll go 5, 6, 7, 8, so we'd be back here again. So I to the 7th to the 3rd, a power to a power, you would multiply them. So this is equal to I to the 21st. So you could do that and just keep the pattern going. So we stop at 4 and go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So my answer is going to be I. But there are other ways you could do it. We can say, well, hey, I to the 7th, that's I squared times I squared times I squared times I to the 3rd power. And I think I squared is the easiest one, which it's actually the most important one to memorize. I squared is negative 1. So this is negative 1 times negative 1 times negative 1 times I. 2 negatives cancel to give us a positive 1. So this gives me negative I to the 3rd power. So I raise each of these to its own 3rd power. So that's negative imaginary 1 to the 3rd power times I to the 3rd power. Negative 1 to the 3rd power is negative 1. I to the 3rd power, well, that's I squared times I, which I squared again is negative 1. So this is negative 1 times negative 1 times I, which equals, these eliminate to give me just I. So that was a really long way of doing it. I think the much faster way would be to just keep going like I did before. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, giving me I. And finally, I squared squared. So again, you should know I squared is -1. And if I square -1, I get 1. Or you can say, okay, well, 2 squared is 4. So this is I to the 4th, which also equals 1. And actually, your calculator can do most of these calculations for you. Not all of them, so you do need to memorize that pattern again, but it can do most of them for you. So if you press second and the period button, it's the bottom middle button, and then select it's the caret button, that's how you get your exponent. And then type in a number for the power, hit enter, and it will give you the answer. So some of these are done for you. So I to the 1st equals I. You can see I squared, it tells you it's -1. So it's super great that your calculator tells you because you need to know that. I to the 9th, it tells you it's I. So like this really long one, I to the 7th to the 3rd power, let's see if our calculator tells us. So it's second period to get the I, and then raise it to the 21st power. Yeah, it tells you I. Or the way that our question was I to the 7th. Oops. I to the 7th to the 3rd, and we get same thing, I. So your calculator does most of these for you, which is super helpful. So that's all for notes 2.2. So now you can go ahead and